Just like in polar coordinates where you had a area form with the r dr d theta, in spherical coordinates we have this volume form where we get this rho squared sine of phi d rho d theta d phi. That's how we use our spherical coordinates, our volume form, to be able to calculate the volume of these objects. So let's do an example. Suppose we are asked to find the volume of the region inside the sphere x squared plus y squared plus z squared equals 4z, and above the cone z equals the square root of 1/3 x squared plus y squared. Well, how are we going to be able to do this? Well, first of all, let's think of a sphere and change everything to spherical coordinates. Well, x squared plus y squared plus z squared, that is just, we know, rho squared. And this is 4 rho. And then what is z? Is rho cosine of phi. There we go. Simple equation so far. Now, for this other equation, for the cone, we could just start it off by having a rho cosine of phi, and this is equal to the square root of 1/3. Now, what is x? Well, x is rho cosine of theta sine of phi, plus all of this squared, plus rho cosine of phi, sine of theta, sine of phi, all this quantity squared. 1/3 distributed. Well, we distribute out our squared, and we get 1/3 rho squared cosine squared of theta sine squared of phi plus rho squared sine squared of theta sine squared of phi. I'm going to just put a half out here, make it simpler. Then, well, we have a cosine squared and a sine squared. Luckily, that reduces, and we get 1/3 rho squared sine squared of phi plus rho squared sine squared of phi, 1/2. Well, luckily we can reduce that as well. And this is 1/3, well, 2/3 rho squared sine squared of phi, 1/2, which then we can reduce that and say square root of 2 square root of 3 rho sine of phi, which the phi's cancel, and we just get, this implies that sine over cosine is just tangent, so tangent of phi is equal to the square root of 3 over the square root of 2, which luckily is just going to mean phi is equal to pi over 3. Nice. That's a really easy equation to deal with. So in spherical coordinates, we have rho squared equals 4 rho cosine of phi, and we just have phi equals pi over 3. So in order to calculate the volume, the best thing to do would be to draw it out to be able to figure this out. Well, the first, we have this sphere, and if we think about kind of how it's shaped from the first one, if we move over the 4z, it's going to be centered at 0, 0, 2. We have this sphere of radius 2 at 0, 0, 2. It's a pretty bad sphere there, but hopefully you get it. And then if we just think of a cone, because it's all just rotating around this pi over 3, this phi equaling pi over 3, what's going to happen is we start at the origin here, and we go out, and we kind of go out and circle around. And so this is pretty badly shaped, but essentially we're going to kind of get a snow cone where we have more, where it's kind of like that. Ice cream cone, snow cone, and kind of like think of it as flipping around. Hopefully that kind of gives a visualization. Pretty bad drawer, so we'll work on that later. Now we have to calculate the volume. Now remember, our volume form, our dV, was equal to what? We had rho squared sine of phi, then d rho, d theta, d phi. And now we need to do our bounds. So obviously in this case, the smallest it's going to be is 0, the rho. Now, depending on phi, like think of it better this way, it's going to change the length that you go out. You could go as far out here, or you could be as close here. But it's really, on this circle, all dependent on phi. Its maximum is 4, and then it's kind of following the phi and kind of the cosine component. So the top is just going to be 4 cosine of phi. Hopefully that helps. Like, think about it. You're coming out, and you need to know how much you're coming out on that phi and decreasing that distance. So theta, well, we go all the way around, so we go 0 to 2 pi. And then phi, we started at 0, right? And we went to pi over 3. And now we just have to calculate the integral. So the integral of rho squared will just be rho cubed over 3, evaluated from 0 to 4 cosine of phi, which that's going to be fun, d theta d phi, and then double integral now 0 to 2 pi, 0 to pi over 3, which we can simplify to, well, I'm just going to write it as 4 cubed over 3 cosine cubed of phi. Now luckily there's a d phi, there's no thetas in this, so actually we're just going to be adding a 2 pi to this. And we have our, oh, sorry, here I didn't bring down, hope you caught me, the sine of phi. So sine of phi still remains, and the integral from 0 to pi over 3 d phi. Now hopefully this made sense what I did here, how I just added that 2 pi. It's because, right, integral of d theta is theta, just plug in the 2 pi and just kind of simplifies that way. So let's pull out the constant and say we've got 2 pi 4 cubed over 3 integral of cosine cubed of phi sine of phi d phi 0 to pi over 3. Then we're going to use our handy old u substitution with u equals cosine of phi du would equal negative sine of phi d phi. And we plug things in, and we are going to end up getting the integral from what's cosine of 0. Well, that's going to be 1, but I'm going to flip it up top to get rid of the negative. And cosine of pi over 3 is just going to be is going to be 1/2, and then we would have u cubed du, and then still our 2 pi and 4 cubed over 3, which when we do our integral here, oh, there's a 1/2 right here, didn't realize it disappeared. So then we just have to do our integral and we're done, which I'll mosey on over here to do that. We get u to the 4th over 4, which luckily we get a cancellation. So I'm going to remove that and have 4/16, so 32 over 3 pi u to the 4th, evaluated from 1/2 to 1, which that just gets us 32 over 3 pi minus and 1/2, so that's 8. 2 to the 4th is just going to be 16, so we get a 2/3 pi, which therefore this should just be equal to 30 pi over 3. 30 pi over 3, of course, simplifies to 10 pi. That would be our solution. Spherical coordinates made this a whole lot easier. If you look at this, kind of follow these steps, and you'll be able to integrate things the spherical way.